Okay, so I'm going to demonstrate another Z80 assembly program I wrote. Last time I showed the Z80 calculating a Fibonacci sequence. This time it's calculating prime numbers. So I'm sure most of you already know what prime numbers are. If you don't, a prime number is a number that can only be divided by 1 and itself. So for example, 5 is a prime number because you can only divide 5 by 1 and 5. 4, on the other hand, is not a prime number because you can divide it by 4 and 1, but you can also divide it by 2. Okay, so yeah, what the program does is it starts at 2, and which is the first prime number, and it just keeps moving up and calculating bigger and bigger prime numbers. So I actually have still the Arduino reading the data bus and displaying the prime numbers in the list that it's calculating. See, so that's a list right there from 2 to 79. Those are all prime numbers, and it's still working on it right now. So this is a little tricky on the Z80 because of the instruction set. The Z80 doesn't have instructions for multiply and divide. It only has add and subtract. So for example, like let's say you were trying to determine if a number is a prime number. Like let's do 5, for example, right? You could try dividing it by a few different numbers and seeing if something other than 5 and 1 works. And of course you'll find that it doesn't. So that's how you know it's not a prime. But with a Z80, you can't do a division. So instead of division, you have to do repeated subtractions. So for example, if you want to figure out, if you want to write an algorithm in assembly code to figure out if 5 is a prime number, you would first subtract 2 from 5 until the result is negative. And then you would subtract 3 from 5 until the result is negative. Then 4 from 5 until the result is negative. Eventually you get 5 minus 5 equals 0. And when that happens, you know that 5 is divisible by 5. And it's only divisible by 5 and 1. So that's how you know it's a prime number. So you can use that concept to design a prime number algorithm. For example, if you checked, that same calculation on 4, right? You would subtract, 2 from 4 until it either equals 0 or, a negative number. Of course, it's going to equal 0. And that's how you know it's not a prime number, because you're able to repeatedly subtract a number other than itself to get the result of 0. So basically the Z80 assembly algorithm I wrote uses that concept of repeated subtraction to determine which numbers are prime and which numbers aren't. So the thing is, though, as you can see on the list, notice it's taking a really long time for 79, right, and to calculate the next prime number. That's because, the bigger the number is, the more times you have to check using the repeated subtractions, right? So to calculate 79 as a prime number, how did it have to do it? Well, first it had to start out subtracting 2 from 79 repeatedly until the result was negative. Then it had to subtract 3 from 79 repeatedly until the result was negative. Then 4 had to be subtracted repeatedly until it was negative. And you just repeat that process over and over again until eventually you get 79 minus 79 equals 0. And that's how you know 79 is prime. So right now, it's working on the next prime number, but that process is so intensive in terms of the number of computations that it takes a long time. And of course I'm running kind of a slow clock speed here. I mean, slow enough that you can actually see the data bus and the address bus flashing, right? But I mean, it's still, very computationally intensive. I mean, that's why it's taking so long. Of course I could speed up the clock rate, to get it to crunch these numbers faster, but I enjoy watching the LEDs flash away. It's kind of fun to look at. So anyways, that's my prime number program written in Z80 assembly. Maybe I could just show you the code really quick just so you get an idea. Right, so by the way, there's this cool website you can see right here. This is an online assembler, so you can write Z80 code and the website will convert it to a binary file, and you can download that and program it to an EEPROM. I think I talked about that last time, but just if you are interested in Z80 assembly programming, this website is pretty good to have. So there's my assembly code. Another interesting feature of this is unlike my Fibonacci sequence program, which was constantly pushing numbers to the stack and putting them back in the registers, this program doesn't use the stack at all, which means it doesn't use the RAM at all. So that's because the stack, I'm aiming my camera at the ROM and the RAM down here. So on the right is the ROM, and actually you can see that the NTE 2764, that's the EEPROM, and you can even see the little electrical tape over the UV window. But you can see that the green LED shows that the ROM is being selected. And you can see that on the left side of the screen, that green LED that is not turned on, that's the LED that indicates that the RAM is being selected. So this program is constantly reading from the ROM and never writing to the RAM. So, and that's because it's using, the really small addresses, which you can see on the address bus, those 16 red LEDs. It's only using those, what that looks like address bits 0 through 6. Yeah, so it's only using small addresses. When it uses the RAM, it uses the high addresses. So those red LEDs on the left that aren't flashing, like those are the addresses that the RAM uses. So, and they're not even being used by this program. So that was just another interesting feature of this prime number program, is that it really doesn't even rely on all of the hardware in the computer. It's not using the RAM at all. It's just using the EEPROM. So anyways, I think I've said about all there is to say about this for now. But I'm pretty happy that it works, although it is kind of slow. It's computationally intensive. It takes a long time to calculate prime numbers, especially the really big ones. All right, thanks for watching.